In this lesson, we are going to introduce quadratic residues and start to lay the foundations towards what is known today as the law of quadratic reciprocity, which Gauss called his aurum teorema, his golden theorem. So this result was first proven by Gauss in his Disquisitiones Arithmeticae, the same book that introduced us to modular arithmetic. And in that book, Gauss proved some of the results we have seen in this course, including Wilson's theorem using modular arithmetic, Fermat's little theorem, Euler's theorem. But those were results that were already known up to that point. What made Gauss famous was the proof of the law of quadratic reciprocity, since it was a long-standing conjecture due to Euler in 1744. And so what I want to do at the start of today is set the context for why this result is so important before we actually get there and motivate the terminology and notation that we are about to introduce. So let us go back to our favorite writer of marginal notes, Pierre de Fermat. So at the start of the term, I mentioned this result, Fermat's theorem on sums of squares. And what it says is that if we have a prime number, then a prime number can be written as a sum of squares if and only if p is congruent to 1 mod 4. First written by Fermat in 1740, so it's also known as the Christmas theorem, since Fermat wrote this down in a letter to Mersenne on December 25, 1640. But of course, as we are very well aware, Fermat did not include a proof, and throughout his lifetime, he actually challenged mathematicians to come up with a proof, but he would never give the result the way that he had supposedly proven it. In addition to this result, Fermat also challenged mathematicians to consider which primes can be written in the form a squared plus 2y squared, or I should just keep the notation as above, a squared plus 2b squared, and p is equal to a squared plus 3b squared. And so Fermat wrote a series of letters to other mathematicians of his time, challenging them to not only just prove the sum of squares theorem, but more generally these results about which primes can be written in this form. Of course, never produced a proof, just empty words. And now let's go ahead, fast forward a good 80 years from this point. So now we are going to be in 1726. So 1726, Euler receives his PhD. From the University of Basel. And in 1729, he first learns of Fermat's conjectures. So 3 years after getting his PhD, Goldbach informs Euler in a letter that Fermat had supposedly proven. And so this is a result we have not talked up to this point, that if we took the number 2 to the 2 to the n and add 1, that this is always prime. For each natural number n. So let's see if this is true. Okay, so we plug in 1, we have 2 to the 2, 4, plus 1, 5. Okay, that's prime. What if we plug in n equals to 2? We'll have 2 to the 4, so 16, plus 1, 17, also prime. So you can go ahead and continue doing this. The problem is, of course, these numbers are going to grow, because then we're going to have 2 to the a plus 1 when we plug in n equals to 3, but that's also going to be prime. And so Fermat said to have proven this. And up to this point, every statement that I have mentioned pertaining to Fermat ended up being true. But of the 48 marginal notes that Fermat claimed to have proven, not all of them were correct. Case in point, this result here from 1729. Something to keep in mind is Euler was not a number theorist. Euler initially got his initial work was in what we would now call analysis, the foundations of calculus. And that's where he got his start. But upon getting this letter from Goldbach and learning of this result that Fermat claimed to have proven, Euler began to buy the right books that contained the letters, correspondences that Fermat had written in his lifetime, as well as the copy of the Fundus Arithmetica with Fermat's original marginal notes. And this began a lifelong obsession of Euler to prove or disprove the many statements that Fermat claimed to have done without any justification. We've already seen one of his arguments, namely Fermat's ditto theorem, which Euler proved. But in 1732, we actually see the first result towards this direction of settling results due to Fermat. So in 1732, Euler's first work in number theory showed that this theorem that Fermat claimed to have shown is false. So specifically, Euler shows that 641 divides 2 to the 2 to the 5 plus 1. And so this here, so we have 2 to the 32 plus 1. This is not a prime number. Therefore, this theorem that Fermat claimed to have proven is definitely false. And this is why we have to be very skeptical of all of Fermat's claims. In some cases, they are true. In some cases, they are not. And as Gauss famously said, to quote Gauss, Fermat came upon his results by induction. He did examples, and he came up with a pattern, and anyone can come up with examples. Proving them is a much harder thing. And in the same quote, which we're going to see exactly how Gauss stated, of course, translated to English, Gauss credits Euler with him dedicating his life to proving as many of Fermat's original claims as possible. So 1732 marks the very first work in number theory for Euler, and it was this result. And in 1749, Euler will prove the sum of squares theorem, which we will be proving this coming Monday. And so on Monday, we will have the tools necessary to prove the Fermat sum of squares theorem in the same way that Euler did initially. And so that's the plan for this coming Monday. So we're going to prove that result. But in the process of getting to this theorem, Euler conjectured a result in 1744. So this is, I'm going to put over here Euler's conjecture. And this is what is equivalent to the law of quadratic reciprocity, or the Auron theorem, Gauss's golden theorem. And that's going to be the main focus, this proving this conjecture of Euler for the next couple of weeks. So what is Euler's conjecture? In order to state it precisely, we first need to introduce some notation. So specifically this new notation here, which looks like a fraction, but it is not. So we call this here the Legendre symbol. And so the way that we read this is as following. We're going to say that this is Q on P. And so what this notation means, and we're going to be showing this more precisely later, is that by definition, this is equal to 1 if and only if there exists some integer x such that Q is equal to x squared mod P. So in other words, the congruence class of Q is equal to the congruence class of x squared in the integers modulo P. So we're looking at the perfect squares mod P. So what Euler conjectured is that Q on P is equal to 1 if and only if P is congruent to plus or minus beta squared modulo 4Q. So this is what would be proven by Gauss and is known today as the law of quadratic reciprocity. And so we'll be proving this result in a couple of weeks, as I mentioned. But the way that Euler came about this conjecture is in the process of trying to prove the two statements of Fermat, namely the sum of squares theorem, and the other statements pertain to which primes can be written as a squared plus 2b squared and a squared plus 3b squared. So he realized early on that in order to prove these results, he needed to prove this statement in very special cases, but it seemed that this here should hold in generality. So when he proved the sum of squares theorem in 1749, he actually proved a special case of this result. In 1759, he was able to prove that the primes, which can be written as x squared plus 3y squared, are precisely those where we have that p is congruent to 1 mod 3 or p is equal to 3. And in 1772, he was able to do the case when p is equal to x squared plus 2y squared and show that that happens precisely when p is congruent to 1 or 3 mod 8. And while we will not be proving these two results as part of our course, they are optional results that you can investigate further as part of your final project, the final paper for the course. So how does all of this come back to this conjecture? And it's subtle, because at first glance, it does not appear that we need to focus only on the perfect squares. After all, we see that here we have a 2, here we have a 3. Sure, we have x squared and a y squared here. But as we go through the original argument that Euler made for the sum of squares theorem, we will see how this is intricately connected to this conjecture. So before we move on into our discussion of quadratic residues, let me just venture a bit more into the timeline of the proof of Euler's conjecture by Gauss, since it allows me to also make a plug for Caroline's analytic number theory course next term. So Euler conjectured this, of course, in 1744. In 1797, Legendre published a proof of this. But unfortunately, the proof was incorrect. So Euler's conjecture. So proof was wrong. But unbeknown to Legendre, Gauss had already proven Euler's conjecture the previous year. So in 1796, Gauss proves Euler's conjecture, but he did not publish that year. That publication came later, and the publication that was available to everyone, Discussiones Arithmeticae, did not happen until 1801. So Gauss publishes. But something important to keep in mind here is that Legendre's proof was incorrect, but that's not to mean that he had not done things that were valuable. While the proof contained a major flaw, in that he assumed something that had not been proven at that point, Legendre's proof laid the foundations for many of the ideas, was built on ideas that he had developed over a span of many years, dating back to 1785. And starting in 1785, Legendre started working on Euler's conjecture and proved results getting closer and closer to getting a proof of this result. And from that, Gauss benefited tremendously. But of course, the fame goes to Gauss, and rightly so. He was the first one to publish a complete proof. But in Legendre's eyes, he felt spited, because Gauss got all the fame, yet he had spent over 12 years working on proving this conjecture of Euler, and dedicated an entire aspect of his career just trying to develop the tools necessary to prove this. And so for the remainder of his life, Legendre actually, in conversation, whenever he had the chance, would talk badly of Gauss as someone who would take credit for other people's work. But what happened with Legendre's proof, and the reason it was incorrect, is that he assumed the following result, which would not be proven until 1837 by Peter de Richley in his thesis. And what it says is, if you have a natural number a and n that are relatively prime, then there are infinitely many primes, p, such that p is congruent to a mod n. So we call this Dirichlet's theorem on primes in arithmetic progression. Another way of saying this is that the congruence class of A is equal to A plus Kn, where K ranges throughout the integers, and so that set contains infinitely many prime numbers. So Legendre believed this to be true, did not justify it, and that was the major flaw in his argument. And so it would take almost 40 years, well, it would take exactly 40 years until it was finally proven by Dirichlet. And for those of you interested in taking Caroline's course on analytic number theory, this is a result that is proven in that course. And so here's a picture of Legendre, the only known picture, it seems, of him. And so he just seems bitter in this picture as well, which is quite interesting given the many quotes that he has attributed to him against Gauss. And so here's one of those quotes that he wrote in 1827 to Carl Jacobi. How has Monsieur Gauss dared to tell you that the majority of your theorems were known to him and that he had discovered them as early as 1808? This excessive impudence is unbelievable in a man who has sufficient personal merit not to have need of appropriating the discoveries of others. And if you go through Legendre's quotes, you'll find quite a number of statements similar to this where he would just take any opportunity he had to speak ill of Gauss. And so this was something that he would not let go, because he felt that he deserved equal credit for having established our own theorem, the law of quadratic reciprocity. Okay, so enough of me rambling about the historical aspects. Now let's go ahead and get the foundations so that we can prove Fermat's sum of squares theorem this coming Monday, and in the process also get started on what we need to be able to prove the golden theorem. So as I mentioned, that symbol in Euler's conjecture refers to those numbers that are perfect squares modulo p. So let's go ahead and make that terminology precise. And so we can go ahead and follow this from the discussion we had in our last lesson on primitive roots. So we can look at the polynomial x to the n minus 1 bar in the integers modulo p for any natural number m. But what if we for now focus on not the case when this is minus 1 bar, but when we have g of x is equal to x squared minus a bar, where now a bar is some element in the integers modulo p. We want to ask, if we fix a bar, when does this have a solution? Because if it has a solution, then we have a perfect square. So for example, if there exists an x bar in the integers modulo p such that a bar is equal to x bar squared, then g of x, which is x squared minus a bar, is going to be x squared minus little x squared. But now that's a difference of squares, and so we have x minus x bar times x plus little x bar. So keep in mind our convention for this course. Whenever we see capital X's, or capital Y for that matter, we are looking at variables, whereas the lowercase x, y, z's, we are considering them as actual elements. So in this case, lowercase x bar is an element of the integers modulo p. And so we would have that the roots of g of x will be precisely lowercase x bar and the negative of it. So we're going to go ahead and study this polynomial. And to do so, we're going to first make a definition so that we don't have to say perfect squares. We're going to now introduce a fancier word, which entails the same exact thing. And so we will say that if we have a natural number n, and a bar is a congruence class in the integers modulo n that is non-zero, we will say that a bar is a quadratic residue modulo n if there exists a b bar in the integers modulo n such that b squared is equal to the congruence class of a. And so that's just what we had here, where I was writing lowercase x instead of b. And then, in the case that there is no such b bar, we will say that a bar is a quadratic non-residue modulo n. Our first result for today will have us consider the case when p is an odd prime, and we're going to go ahead and assume that a bar is a quadratic residue in the integers modulo p, and we want to show that there are exactly two elements, x bar in the integers modulo p, such that x bar squared is equal to a bar. But the proof of this we actually just did in our sketch where we looked at the g of x. So let's see why. That's almost enough for the proof. So here's the argument. So by assumption, we know that a bar is a quadratic residue. So since a bar is a quadratic residue, so I'm going to abbreviate to the quadratic to QUAD. So since a bar is a quadratic residue, there exists a b bar by definition in the integers modulo p such that a bar is equal to b bar squared. But what if we consider the polynomial g of x where we have x squared minus a bar? So next, we have, since the integers modulo p is a field, so we have that p is a prime number, so the integers modulo p is a field, the Lagrange's theorem implies that g of x, which is equal to x squared minus a bar, has at most two roots. So we have that g of x has at most two roots, but now what if we substitute in? So since g of x is equal to x squared minus a bar, which is x squared minus b bar squared, which is now a difference of squares, so we have x squared plus b bar, x plus b bar, x minus b bar, we deduce that b bar and minus b bar are roots of g of x. Now, this is not enough to conclude the proof of this, but for homework, you'll show the following. Since b bar is not equal to negative b bar, so this will be shown in your homework. We conclude that there are exactly two elements in the integers modulo p satisfying that this here is equal to this. And so that's what we wanted to prove, so now we are done with our proof. So we know that there are exactly two roots, two elements, whenever we have a quadratic residue. So we know that we can find two elements in x so that x squared is equal to a squared. Similar to how this works over the integers. If we have, say, the number 4, we know that we can look at 2 and negative 2. And more generally, if we have a perfect square, positive and the negative of its square root are the elements that we want to look at to get back the number back. And so this is extending that notion that we are familiar with the integers, but now to the integers modulo p. So now we're going to go ahead and show that if we have a p is an odd prime, that there are exactly p minus 1 over 2 quadratic residues in the integers modulo p. So the proof that I am going to give is slightly different than the one in the book. But I will go ahead and also discuss the proof in the book since it's quite nice and clever. But this one's going to be more explicit in that we lay all the steps that we have. So the idea of the proof that I'm about to show, its start is similar to how we would go about saying how many perfect squares are there how many perfect square integers are there that are between 0 and 100, including 100, but not including 0. So we could go and set it and count down like 1, 2, 3, 4, all the way to 100 and see which ones are squares, but that's too much work. We want to be lazy. So we want to go ahead and just do, okay, we do 1 squared, that will be a square, 2 squared, that's a square, 3 squared, that's a square, 4 squared. And so each of these, by doing it in this fashion, we just get back every single square. But we then stop at 10, because at 10 squared we are exactly 100. And so similarly, we're going to start this proof by considering those non-zero squares of the integers modulo p. So let S be the set of the non-zero squares. But we have a fancy word for this. So let's go ahead and, so we have the set of the non-zero squares in ZP. But just to get us comfortable with the notation, this is just saying the set of quadratic residues. And so every time that we hear the word quadratic residue, since this is a new term, this is just fancy language for saying the non-zero squares of the integers modulo p. So if we consider the set of the non-zero squares and we use that motivation for counting squares that are less than or equal to 100 for the positive integers, then we can go ahead and square all the elements in the integers modulo p. So we're going to be looking at 1 bar squared, 2 bar squared, 3 bar squared. Each of these will be quadratic residues by assumption. They are all perfect squares and they are non-zero. And then the very last element of the integers modulo p, if we order them, is p minus 1 bar. So we have this here squared. And so we have our set S. But now, we want to make the following observation. This is the set of all the non-zero squares, but we know the following. So 1 bar squared is the same as negative 1 bar squared, but negative 1 bar is the same as p minus 1 bar squared. And similarly, 2 bar squared would be the same as minus 2 squared, which is p minus 2, the congruence class of p minus 2 squared. And so more generally, we have that if we took little x bar squared, that this will be the same as minus x squared, which is the same as p minus x squared. Because we have these equalities, we get the following. We can go ahead, so we set this set S, but 1 bar squared and p minus 1 bar squared, these are the same element. So in the set, we are only counting the distinct elements, so we are actually double counting. This doesn't have p minus 1 elements. So we can use this idea to now eliminate the double count. And so we have that 1 bar, we can go ahead and look at 1 bar squared. But we no longer will have p minus 1 bar squared, since that's the same as 1 bar squared. We'll have 2 bar squared, 3 bar squared. But then we continue. But we are going to stop at p minus 1 over 2 squared. So the reason for stopping at p minus 1 over 2 is that we know that p is odd, so p minus 1 is going to be even, so it's going to be divisible by 2. But more precisely, if we look at p minus 1 over 2, note that this here is going to be the same by this deduction that we have here, that negative x squared is the same as p minus x squared. So we know that this here is going to be the same as p minus 1 over 2 squared, so we have this difference will be the same. But if we simplify the right-hand side, and so this will be 2p bar over 2 minus p plus 1. So this is going to be p bar plus 1 over 2. So we have this here. But now that's the same as p minus 1 over 2 plus 1 bar. Because in doing so, we'll have 2 over 2, we'll have p plus 1 over 2. So p minus 1 over 2 bar is the same as its follow-up term, which is going to just happen. It's just going to be p minus 1 bar over 2 plus 1 bar. And so we can go ahead and stop S here. So this tells us that the cardinality of S is going to be at most p minus 1 over 2. Because of course, we still don't know if we are double counting here. We may, it may be the case that we are. So we know that this is at most p minus 1 over 2, but we claim that it's exactly p minus 1 over 2. So we claim that the cardinality of S is p minus 1 over 2, which will establish the theorem. So how do we show this? So to show this, it suffices to show that each element in S is distinct. But now, technically this is a bit ill-defined because S was the first defined like this, and now we have simplified it to this. So this statement is referring to this portion of S. That every element in here is distinct, and so every element in this list is distinct. And it's actually, because that is ill-defined, I'm just going to rephrase this in the following way. That each element in the list, 1 bar, 2 bar, all the way to p minus 1 over 2 bar, is distinct. So this is what we want to show. So how do we show that these are all distinct? And I forgot the squares. Well, let's go ahead and take two elements in here and suppose that they are equal. So suppose that j squared is equal to k squared bar, where we're assuming that j and k are elements between 1 and p minus 1 over 2. So we're choosing j and k to be integers such that they are between 1 and p minus 1 over 2. And so we're assuming that their squares are the same. If we subtract k squared on both sides, we get the following. J bar squared minus k bar squared is equal to 0 squared. But that's a difference of squares, so we have j plus k square. So this here is going to multiply to j minus k. And so this is equal to 0 bar. But now, recall that here we have, this is equal to 0 bar. We're working over the integers modulo p. So this here says that p divides j plus k, or p divides j minus k, by Euclid's lemma. Or if we prefer, we can use what the book calls the modular Euclid's lemma. And so that's this statement over here, which just restates the original lemma of Euclid's. If p is prime, and we're working over the integers modulo p, then x bar times y bar is equal to 0 bar implies that x bar is equal to 0, or y bar is equal to 0. So this tells us that this here is equal to 0, so j is equal to negative k bar, and similarly j bar is equal to k bar. So then by theorem 835, we have that j bar is equal to negative k bar, or j bar is equal to k bar. since we know that j and k are integers between p minus 1 over 2, we have that j bar cannot equal negative k bar. And so j bar is equal to k bar, which shows that each element in the list, which I'm going to go ahead and label now star. So in the list star is distinct. And so if they are distinct, that was what we wanted to show, because if that's distinct, that tells us that now the set S, the cardinality of S, is exactly p minus 1 over 2. So I'm going to go ahead, write that just in the corner over here. So we come up over here. So now this implies that the cardinality of S is p minus 1 over 2, which concludes the proof. Now we are done. We have shown that the set S, which corresponds to the quadratic residues of the integers modulo p, has exactly p minus 1 over 2 elements. So now that we have seen a proof of theorem 11.1.3 that does it explicitly, let's go ahead and follow the book's proof, which uses the theorem 11.1.2, which tells us that if we have an a bar in the integers modulo p, which is a quadratic residue, then there are exactly 2 elements x bar in the integers modulo p, such that x bar squared is equal to a bar squared. So here's how the proof goes. So we're going to start the same way. So consider the set S of quadratic residues. So we have 1 bar, 2 bar, all the way to p minus 1 bar. But we're going to be squaring each of these terms. So now this is the set of all the quadratic residues. The set of quadratic residues of the integers modulo p by the theorem so the number here is 11.1.2. There are exactly 2 distinct elements just go ahead and call them x bar and y bar, such that x bar squared and y bar squared are the same. So that's a way of interpreting that result. So in this list, since we're looking at the squares of these congruence classes, we know that there are exactly 2 of these that their squares are going to be the same when we look at them as in the integers modulo p. So we have that this is double counting. So each element in the list one bar, 2 bar, all the way to p minus 1 over 2, to p minus 1 appears twice. And so the cardinality of S is going to be p minus 1, because the integers modulo p minus 0, that's p minus 1 element. And now we remove the double counting, we have over 2. And so we are done. So that's a shorter and nice proof of this. So now we have another argument for showing that we have exactly p minus 1 over 2 quadratic residues for the integers modulo p. So with this, let's go ahead and prove the following corollary. So the corollary tells us that if we have an odd prime number p, then there are exactly p minus 1 over 2 quadratic non-residues in the integers modulo p. And so the number of quadratic residues is equal to the number of quadratic non-residues in the integers modulo p. But now the proof is going to be automatic. So the proof is the following. So let S be the set of quadratic residues in the integers modulo p then the set T of quadratic non-residues of the integers modulo p is going to be the set difference of the integers modulo p minus S, the set of the quadratic residues, and 0. Because if we go back to our definition, for quadratic residues and non-residues, we're making a statement about the non-zero terms. And so when we say a non-residue, we're looking at a non-zero element of the integers modulo p. And so when we're looking at this, we're looking at the set difference of the integers modulo p minus S union 0. But we know that S does not contain the congruence class of 0. So this tells us that the cardinality of T is the same as the cardinality of the integers modulo p, so in this case p, minus the cardinality of S plus 1, but the cardinality of S is p minus 1 over 2, and then we're going to be adding a 1 for the 0. So that's going to give us p minus p, and then we go ahead, we're going to have p plus 1 over 2. And so now we can simplify this and get p minus 1 over 2. And so we get that the cardinality matches up with what we expected. So we have this right here. An easier way of visualizing this, of course, is we have p minus 1 over 2 is half of the non-zero elements. So the other half has to be a non-residue. And ta-da, we got the corollary. And so that's really what we have done by writing this out in detail. And so that tells us exactly that we have, in the case of quadratic and non-quadratic residues, the same number. So we have the same number of squares as the number of non-squares, but specifically non-zero squares and non-zero non-squares. So let us go ahead and define the Legendre symbol that we used earlier to define Euler's conjecture. So Legendre does get credit for this. His notation for the law of quadratic reciprocity is much, much simpler than the one that Gauss introduced. And so that's the notation that has become standard throughout mathematics for discussing the law of quadratic reciprocity, specifically when a number is a perfect square or is not a perfect square. And it's similar to how Newton and Leibniz, they both developed their own terminology for derivatives and integration. Yet it is Leibniz notation that we use in calculus. So in calculus we use dx, whereas Newton's notation uses a dot on top of the functions, as opposed to the f prime or like x prime in this case. And so Newton's is clunkier. Leibniz's notation is preferable, and that's the one that has become standard for us. And so similarly, no one uses Gauss's original notation, but instead we use Legendre's notation. And so here's how we define this Legendre symbol. So we have a odd prime p, we have an integer a, and so we say that a on p is defined as follows. We say that it's equal to 1 if the congruence class of a is a quadratic residue modulo p. So in other words, a is a perfect square mod p. It's equal to negative 1 if a is a non-zero non-square modulo p. And finally, we say that it's 0 if A is divisible by P. And so even though we do use this fraction notation, in this course it will be clear from context whenever we use this notation that we are referencing the Legendre symbol as opposed to an honest fraction. So now with this notation in mind, let us go ahead and prove the following theorem. So if P is a knot prime, we have that A and B are integers, and A is congruent to B mod P. Then we have that A on P is equal to B on P. But now the proof follows because we know that A is congruent to B mod P is equivalent to A bar equals B bar. And the Legendre symbol is a property on congruence classes. So we have that the proof follows since A congruent to B mod P is equivalent to saying A bar is equal to B bar in ZP. And the Legendre symbol depends on congruence classes. So we're done. Indeed, if we take A bar to be a non-zero perfect square, so in other words, A bar is a quadratic residue, then B bar by definition must be a non-zero perfect square. Same for non-residue, and similarly if it's divisible by P. If A is divisible by P, then B is divisible by P. So we are done. We have our proof of the theorem that whenever we use the Legendre symbols, it's preserved under congruence mod P. To finish off our lesson for today, let us go ahead and consider the following exercise. So we want to prove that if we have a natural number whose digits add up to 15, then n is not a perfect square. So how do we prove this with what we just covered about quadratic residues? So here's how. So if n is a perfect square, so let's go about this by contradiction. So towards a contradiction, suppose n is a perfect square. So if n is a perfect square, that means that there exists some integer k such that n is equal to k squared. So we have n is equal to k squared over here. Now let us ask, do we have any results at our disposal that tell us how a natural number relates to the digits, to the sum of its digits? And so here's where we want to recall one of the first results we proved when we talked about modular arithmetic, namely the divisibility properties for being divisible by 9. So I'm going to write this down here to recall. 9 divides n if and only if the sum of the digits of n is divisible by 9. But we actually showed in that proof it was even stronger than this. We showed that n is congruent to m. Actually, let me not use m. Let's use L. So in that proof, we actually show the following, that n is congruent to L mod 9 if and only if the sum of the digits of n is congruent to L mod 9. So if we use this result, we get the following. Then n, we know that the digits add up to 15, so n is going to be congruent to 15 mod 9 by using the result right here. But 15 is the same as 6 mod 9. In this lesson, we were looking at, when dealing with the Legendre symbol, we were looking at the case when p is an odd prime. But our notion of quadratic residue does not depend on it being prime, but just that we have a natural number. So what we now have is, we have 6, that n is congruent to 6 mod 9. So what we have to ask, is 6 a quadratic residue? Because the way that we set this up, we know that 6 is going to be congruent to k squared mod 9, since we know that n is equal to k squared. So n is congruent to 15, then k squared must also be congruent to 15, so it must be congruent to 6 mod 9. So in other words, n is a quadratic residue modulo 9. And here we are only looking at a case when it's 9, but the main takeaway from this proof is that whenever we have a perfect square, that perfect square will be a quadratic residue modulo every natural number that is relatively prime to n, since we want to eliminate the zero cases. So we have n is a quadratic residue modulo 9, but the quadratic residues modulo 9 are, so we have 1 squared, 2 squared, 3 squared. So if we compute each of these and then reduce mod 9, we're going to get the following. So here we are, we've gone ahead and computed all the elements from 1 through 8, so all the non-zero elements. But of course, 3 squared is going to be 0, and 6 squared is going to also be 0 modulo 9. But now we have that the quadratic residues mod 9 are 1, 4, and 7. So in other words, 6 is not a quadratic residue. So 6 is not a quadratic residue, which implies that n is not a quadratic residue, which is a contradiction. Because we got that n was a quadratic residue by the assumption that n was a perfect square, and so we are done. So that concludes the proof for this. And so that concludes it for quadratic residues for this lesson. So our next lesson will have us continue to lay the foundations so that we can talk about how Euler went about proving the case when Fermat's sums of two squares theorem. And so we're going to be proving that on Monday, but on Friday we're going to be talking about what is known as Euler's identity. And that will be a crucial step towards getting to that statement of Fermat that Fermat claimed